Good evening, everyone. I am Bandhuka Kudu, Technical Events Coordinator for Civil Engineering Sectional Committee. And this is the 8th session of our lecture series on structural design of highway bridges. And I would like to take a moment to express my deepest gratitude for your willingness, Professor, to conduct this lecture series. Your expertise and passion for your subject matter are truly inspiring. And I know that your insights will be valuable to all of the participants. And for the participants, I would like to remind to rename your login name with your membership number. Then it is easy for IESL to trace your participation. And over to you, sir.
Just one moment, Bandhuka, start now.
Yeah.
So thank you very much for the introduction, Bandhuka. And today, first I'll share the screen. So basically, today we'll concentrate on composite bridges. And if I use the same presentation because it covers that particular aspect as well. Before that, I would like to tell you that there was a great deal of enthusiasm regarding this particular form of bridge construction, and one of the participants asked about this particular information. They asked about it, and I shared some of the research papers that we have published. So I will try to find some more information because one of the students who did the work is now in Brisbane. So I can ask him to find some more information, because we did this research project over about 3 years with the undergraduates. Because and also if you go through the transactions of IESL, you can find another research paper that we published in year 2000 at IESL transactions. So that's another paper that you can look for, and it should be available online. Right. So this is something that you would have seen probably. That is, we use this particular structure, and the reason is this particular man-made island in the middle of Duva Reservoir, and the length of this bridge is 300 feet. The width is 12 feet. The lorries and tractors can use this one. And this was constructed during a time when this reservoir was emptied for desilting. So because of that, we had a small advantage when we were constructing the foundations. Foundations are all combined footing with columns coming up, and I think 3 columns came because we used the total width was about 12 feet. And the other important thing is the cost. Cost was only 6 million, and it was constructed by a normal contractor, maybe just a experienced mason running his small construction company. He did the construction of the bridge. Cost was less than 2,000 rupees per square foot. Right. So those are the important things, and I think this will be a very good solution whenever, especially the rural bridges. One of the beauties actually when you go for this particular method, we are actually removing all the material that we consider as cracked. So all this material in concrete, especially reinforced concrete, we consider all the material below the neutral axis is cracked. So basically what we do is all the cracked concrete is removed, and in doing so, we reduce the weight of the bridge, but we retain the stiffness. The reason is every 1.5 meter or 1.8 meter, you get a beam. because there's a beam, we can retain the stiffness of the structure, but we remove the unnecessary concrete, and in doing so, we reduce the weight of the structure. So actually, the weight of the structure can be about 50% of the live. But if you look at even the kind of bridges we are going to discuss today, you will find that the weight of the structure is more than the live. Always that is the case. Whereas in this particular structure, it is less. And we have actually done, you can do various things. And one of the things I can just stop share and show you. Because, now when you are casting reinforced concrete, it is difficult for us to cast very, very, very different shapes. So what we do is we go for a rectangular beam, maybe 350 wide, and the depth may be about 600. I'm talking about bigger spans. And but we know for sure that a shape like this would be much more efficient. Shape like that would be more efficient. But the problem is, how do you create a shape like that? So one of the options that is available is here you will have the beam cast like this, and it will have some reinforcement going like this. So one of the possibilities, you can place some steel bar here and place two bamboos. Place two bamboos with steel in this direction also. So once you create steel like this and fix some bamboos, you can automatically remove part of the concrete. The reason to do this is that, anything in this area is cracked in this beam. Any concrete in this area is cracked. So anything if it is cracked, remove that concrete by using a void form. So one of the easiest void formers that we can get at a reasonable price is bamboo. But when you do this, actually bamboo also can contribute to the tensile strength, because bamboo will be, because we are keeping some spaces, the concrete will be filling up all these spaces. And when you are placing the bamboo also, bamboo is something tapering. So what we do is, when you fix one bamboo this way, the other bamboo will be the other way. So you can actually create void form, use bamboo to create void forms. And when you are using the bamboo, you don't clean it too much, so that, it will be little rough. And there will be good bond, because it's tapering in two different directions. There will be good bond. And actually bamboo can contribute to the tensile carrying capacity needed in the beam. And you can actually get a lighter beam, but which has a higher flexural capacity. So these are all different options that you can easily try. One thing is, this will reduce concrete. The other most important is not only reducing concrete, but reducing weight, because we have to lift it and place it, so reducing weight of the beam. And also it provides additional flexural capacity. But when you are using the bamboo, we can actually place it under a fire and heat it up. So you place it under the fire and heat it up. So the idea is, when the bamboo is heated up, the starch and protein in the bamboo will be converted to a different form. And once that transformation occurs, bamboo can become a very strong material. So that's another important thing you can think about. And so this is Civil Engineering Sectional Committee, and today is 25th for 2023, page number 1, right? So we can actually have place it under a fire, and heat it up to about 180 degrees. So at that temperature, you can actually get this transformation in the starch. And you might ask, how do you get this technology? And when you play LA, you use this bamboo, and that bamboo is not just from a tree. It's you cut it and then you place it under a fire, and you will make this transformation to happen. And the final result is this bamboo can last 20-30 years without being attacked by pinhole borers. So you don't get pinhole borers attacking it, but bamboo is a material that is very easily attacked by pinhole borers. But the moment you do this heat treatment and get this starch transformed to a different form, you will not get any of these pinhole borers attacking the bamboo. So that's a great advantage, because one of the weak points about bamboo is it can be easily attacked by pinhole borers. So and some call it kiriveya. Some call it in Sinhala, they call it kiriveya. Kiriveya is the kind of pinhole borer that is very tough insect. You can even if you use wood preservative, it will hide somewhere and escape. But once you heat it up, it will never come to the bamboo. So that's a kind of advantage you can gain when you are using bamboo. And I will share the screen again. So here you can see this formed with a grillage. Another day I will show you how to use grillage analysis as well. And the reason is this Sima Malake, which is a very nice thing to go and see. And also these days now there's another Buddha statue also coming up at this particular place. And all the information that you need, including the reinforcement, is given in this chart. And it comes with a research paper, so you can easily use these values as a starting point. Right. So today our attention will be on this particular type, and that is sourdough slab bridges. Sourdough slab bridges. So the bridge looks like a slab, but it is not a slab. So it looks like a slab, but it is not a slab bridge, right? So basically, how we form it is by using precast beams, and we place the precast beams as inverted T, or this particular type of shape, because they from different companies, or even from the same company, you can get different shapes. And this used to be one of the earlier shapes, and then they went for this particular shape. So the idea is, you get a certain depth, and you can easily get a chart. I can actually share that particular chart with you, and then you can see there's another form. This is called M beam, because here we are not filling up. This for 16 to 29 meters length, but the theory is applicable for both. But today we learn the theory with this particular form. We'll learn the theory with this particular form, and it is applicable to this form, and it is applicable to this form as well. This is the latest what we call Y beam. And again, you can, for any of these, you can get a chart like this, And on the chart, you get the spans possible as well. And this is with a 1000 millimeter, 1000 millimeter centers, and this is with 2000 millimeter centers. So you can actually keep a gap. Right. So this is how the bridge looks like. This is the Y-beam variation. And when people use this for the first time in 1960s with pre-stressing, they actually thought it's very good if they can form a slab without formwork. It's very good if they can form a slab without formwork. So they went for this particular form. But later they found that this particular bridge is too heavy for longer spans. So this is for about 6 to 18 meters. But then they developed this particular one from 16 to 29 meters. But the problem is that here you can see the bridge is not accessible for any inspection. You can't see it. So then what they thought was, okay, let's see whether we can go for another form. And they came up with this one because here you can see the bottom flange is only 7. So when you place them at 1 meter interval, you get a gap of 500 millimeter. That is good enough for any inspection, bridge inspection, or even to apply any epoxy or whatever the coatings. That distance is good enough. And if you look at the span, again, you can see the maximum span, you can go up to about 31 meters. 31 meters. So these are the 3 variations that we can get. And I'm going to present you how we look at it. So first, we'll start with this particular type. And so basically, I'm going to now shift to the white paper. So, just make a view of this, or you can even take a photo of this particular screen, because when I explain, then you can always refer back to the photo that you have on your phone. So if you have a phone, just take a photo of this, so that you know, when I explain, if you want to have a look at this again, you can easily do so, right? So, so what I do is I'm going to stop sharing now. If you are on a computer and you have a phone, please take a photo. Right. So I will anyway come back to that. So we see what's going to happen. So what we have is a beam. What is the advantage? Up to 18 meter, we don't need formwork. We don't need formwork. So what we do is we place this bridge beam, and this beam is actually done in such a way that when you are doing the construction, you don't need any kind of formwork, right? So we place the beam, and you place next beam. So that means when you cast on the long line method, when you cut the tendons, it will move on like this. So you get MD1. You get a moment, because that is, this moment is due to self weight. Moment is due to self weight. Okay. So then what we do is we'll place the beams like this, and with about 100 to 150 millimeter cover here, we'll place concrete. And sometimes, you know, people even use void formers here, but that is considered as one of the, not a very appropriate one, because sometimes, you know, to reduce the weight, you can even use polythene filled up with sawdust and use a void form. But you know the density of concrete is very high, and it's very difficult to control this void form. So because of that reason, it's not popular at all. So people like it this. So what happens is you get a beam. And it's filled with concrete, and the width of this is 500 millimeters, 495 millimeters. So we say 500 millimeters. So every 500 millimeter you get a beam like this, and so basically we get this, and then what we do is we get something like this, and then we get some additional weight on it, and that will give rise to MD2. Still no composite action. It's just a pre-stressed concrete beam carrying the construction loads. So we get this. Now the concrete starts hard. So all this concrete will become one concrete, and there's a tie bar as well. There's a tie bar. So as far as this, if you consider the way that the slab beam this way, the depth will be this, because here you can see there's a discontinuity. So the depth of the slab is slab in transverse direction. Transverse direction. But if you look at the slab in the longitudinal direction, you get full depth. So this is the slab depth in longitudinal direction. So you get two different depths, right? You get two different depths. So the first thing is, first thing we have to understand is when you are casting this with long line method, we are going to get self-weight active, that is MD1. And when you are placing the concrete, before the composite action becomes effective, this beam has to carry the weight of the concrete, this concrete, as self-supported. So that means, still it's simply supported. So MD1 simply supported, which means W L squared over 8 type situation. MD2 still simply supported. Okay, so still it's simply supported. Now we have to see how it's going to behave after this. After this, we are going to place asphalt, and we can even get MD3. So after this, this is going to become a bridge, and we are going to have beams like this. So we are going to get many beams like this. Get a bridge like this. Now you can see this is only 0.5 meters. So if you are going to have a grillage beam for every 0.5 meters, the grillage can become a very complicated thing. So what we generally do is, we say this is one beam, this is another beam. So we place the grillage beams at the center. So we are going to get grillage beams at the center like this, as at 1 meter. At 1 meter. So we don't really worry too much about these things, because what we do is we create a series of beams to represent the slab, because once we get the total moment, we can divide it by 2 for when you are designing 1 beam. So this way also we can use either 1 meter or 2 meter interval, and so even this way at 1 meter, this way at 2 meter, even that is okay. That is not a major problem, right? And then what we do is we have to now look at the properties. So if you have a beam like this, we have to input I value. That is not a major problem. We have to input I value. We have to input I value. That is not a major problem. Why? Because I can be calculated. Second amount of area can be calculated for the whole section. Then for slab bridges, the torsional constant in x direction is given by height cube divided by 6. Height cube divided by 6. Right? But I explained earlier, because we are having this shape, here there's a discontinuity. Here there's a discontinuity. So we have 2 different lines. So we get, we can say Cx, Cy. So this will be H1, this will be H2 cube divided by 6. Because we are getting 2 heights, H2 this way, in the other direction, H1. Then for the torsional constant, C, we get square root of Cx, C1. We get the square root of Cx, C1. We get square root of Cx, C1. So what we do is, we substitute the average value for as the torsional constant for this. So when you are doing, so you have to substitute a reasonable torsional constant, and what we substitute is a value like this. So we'll come to those details in much more detail when we are talking about relay analysis a later day. So when you have a grillage, let's say we have a vehicle. So we have vehicle like this. We can place vehicle anywhere we like. So from the grillage, we get only 2 informations, because when you are doing the bridge, if you look at the bridge section, we get a slab, then we have curbs, we have handrails, and we have asphalt concrete. All those things we can say superimposed dead load 1, and it comes from the grillage. And then you get live load that also comes from the grillage. So this is something that you have to very clearly understand about these precast bridges. Because in the precast bridge, some of the moments come before the composite action comes into effect, becomes effective. So which means they are statically determinate structures. So in composite construction, so moments MD1 simply supported, which means statically determinate. Then you get MD2, again simply supported, and this is the weight of concrete, additional concrete, that is also simply statically determinate. Then you get M superimposed dead load 1, which is from the grillage, because we are modeling a slab. Modeling a slab. What is the importance of slab? We get load sharing. We get load sharing. When it's simply supported, no load sharing because there is no composite action. So when you have the weight of this walkway, pedestrian walkway, that will be distributed over the full width. The parapet load, weight, all will be distributed. So you get load share. And live, again from the village, again we get load share. What is the reason for load sharing? High torsion capacity. What is the reason? Reason is high torsion capacity. So this Civil Engineering Sectional Committee 4, and today is 25th for 2023. So you have to understand this clearly, because you have to understand, until the composite concrete hardens, there is no composite action, and until such time, you don't need a village because it's a statically determinate structure. But the moment the composite action is regained or gained, rather, then you get load sharing. That means you have to analyze it with a village, and then live load also you get high load sharing because of high torsion capacity. And why do you get a high torsion capacity? Because it's a slab. Only there are few discontinuities between the beams. So what happens is when it behaves, the torsional stresses, torsional shear flow will occur like this, and it will come down. It will go like this. But you can see, because we are considering a substantial depth, there's a significant distance between the torsional shear flow. When there's a significant distance between the torsional shear flow, the torsional moment carrying capacity is very high. So this is a very strong structure in torsion. It's a very strong structure in torsion. And so it's a slab bridge. So that's why in the original development in 1960s, which is all close to 60 years ago, they did a lot of development in England for the BS code, and lot of work has happened at Birmingham University and some of the main universities. They did a lot of testing. And actually, even the village method was originally proposed in 1964. So this is not early 1960s, the late 1960s. They did a lot of testing to develop this particular form of structure. And in doing so, they found that this slab bridge is very good because it has very good load sharing characteristics. So basically what you see is that we have to use a grillage, and once you use the grillage, apply the loads, the computer will do the rest. It will give us a torsional moment, bending moment, and shear force. Out of that, what you find as critical is only the bending moment and torsion, bending moment and shear force. The reason is these structures have a very high torsional moment carrying capacity, and you might see that we are placing some reinforcement, the strong bar like 25 millimeter one, connecting all these beams, and that is one of the reasons for that particular bar is also to facilitate the torsional shear flow. So basically they wanted to make sure all the beams are held together. All the beams are held together. So this beam had some slots, And through the slot, you will put a 25 millimeter bar and connect all the beams together. And they found the behavior is very satisfactory, very stiff structure, and ideal. So that is the first development, but we'll come to the second development, that is M-beam, later. But now today we are concentrating on this particular simple form of structure, and we want to see how we are going to analyze it. First, the analysis is not a problem because I showed you how to get the moments sorted out. But once you have the moments, we have to undertake the design. So again, we have to see how we undertake the design in the traditional way, because Eurocode allows you to be little adventurous as well. But we'll analyze it in the traditional way, where we say we like to have it tested for flexure at service conditions. Under the transfer condition and also the live load, full live load condition. So that is the traditional way we did pre-stress concrete, but Eurocode actually allow us to be a little more adventurous and even go to the level that we allow some tension beyond the nominal tension carrying capacity of concrete. And in BS code, these structures were considered as class 3 structures. So in Eurocode, they don't specify class 1, class 2, or class 3. So they simply say that you do the designs whatever the way you want. But it does not say that you can't you have to deviate all the time from the earlier practice. It says it can be anything. So because we are all happy with class 2 type structures, we'll consider that we are going to have a maximum stress, compressive stress, and a reasonable tensile stress allowed, not excessive, under working conditions as well. So that's a reasonable assumption. But later I will show you that we can go even beyond that as well. So that we'll discuss later. But I'm now trying to stick with our traditional way of designing pre-stress concrete structures, and then that method I showed last time by developing the equations as well. So what we do is, we have a beam, we have I value, and it has a centroid, and we can measure y1, y2 this way, y1 this way, and you get z1 as negative, z2 as positive, because we are measuring this side as positive and this side as negative. Upper side is negative. And then we also have to be little concerned about what's going to happen once we restore the composite condition. Now you can see this is the composite situation, and originally we had the neutral axis somewhere here. Now the neutral axis will be somewhere there. Now the distances will be y1 dash will be, y2 dash will be there, y1 dash will be that. So we have to be very clear about this, because we are designing the pre-stress beam. So what happens is, once we place the concrete, it will we fill up all this area. Then actually the chances of this exceeding the compression at working will be very remote. Why? Because we are having a lot of concrete, and the neutral axis also shifts upwards. So there's no way that it can fail in compression, but actually the failure can come in tension under working conditions. So that will be the governing condition. But there's no way that this will become a governing condition. But still, when you are writing the equations, we write the equation not for the composite section. We write the equation for the pre-stress concrete. So still the width is the same. Neutral axis has changed. And then the other important thing is, yes, so you get I2. So we say this is I1, sorry, I. Now I get I composite. Here you get I composite, right? I get I composite value. But still, when you are calculating the properties, I composite is for the whole section. But still, we use I. So Z1 dash will be I over Y1 dash. And it will be negative quantity. Z2 dash will be I over Y2 dash. So this is something again you have to be pretty certain, because here still you have to understand once the composite action becomes effective, what you are changing is the neutral axis, but we are not changing the section. Section is still we are designing a pre-stress concrete section, so section cannot change. We are designing a pre-stress concrete section. Now we can write the equations. So the equation is, first it goes like this, and then later we add, and finally when we do all the loads, it will go like that. And so here the failure will be tension at transfer, compression at transfer, and here the failure will be very unlikely failure, compression at working, but the likely failure is tension at working. So those are the 4 conditions, the failures, right? And in addition to that, we say compression positive, tension negative. We also say anything measured downwards positive, anything measured upwards negative. So that's a sign combination. And last time, if you have listened to the earlier lecture, you'll find that I showed you that once we use this particular notation system, it's very easy to write the equations because it always follows the same pattern. So for that, we'll go to the next page, and that is Civil Engineering Sectional Committee, page number 6, on 25th for 2023, and that is 25th 2023. Now what happens is, we have a section, we apply the pre-stress at an eccentricity, so we get these stressors, we get POA, compression, that means positive, and then we get tension at top, compression at bottom, and PE over Z2, PE over Z1. So that is under transfer conditions. Then we construct the bridge. Now not POA, now RPOA, compression plus RP over RPE over Z2, RPE over Z1, and in this case we get the dead load moment coming, and here tension compression minus MD 1 over Z2 minus MD2 over Z1. So here also you get MD1 over Z2, and then you get MD2 over Z2. Then you get superimposed dead load M superimposed dead load over Z2 dash. Why? Because now the composite action is effective, and what is applicable is not this depth, it actually goes like this over a greater depth. So it goes like this, right? So this has a different neutral axis to this one. This has one neutral axis, this has a different neutral axis. And here this one is M live over Z2 dash. So you get this. So now we can write 4 equations. And if I write the 4 equations, we write the 4 equations. First equation from this one, P over A plus P over Z1 minus MD over, sorry, MD1 over Z1. And here it's going to fail in tension. Should be greater than tension. Tension and transfer. And tension is negative, so this is negative minus 3. Minus 2 is greater than minus 3. So we are saying greater than. And then P over A, bottom 5 is going to fail in compression under transfer. P over A plus P over Z2 minus MD1 over Z2 should be less than tensile stress, compressive stress at transfer. Compressive stress at transfer, right? So this is the equation number 1. It is equation number 2. Now we look at equation number 3. And now we are looking at P over A, RP over A plus RPE over Z1 plus minus MD1 over Z1 minus MD2 over Z1, that is the weight of the concrete that we place, and then minus MD1, MD2 and M superimposed dead load over Z1 dash minus M live load over Z1 dash. This is now equation number 3. So that's how it comes. And the last equation is RP over A plus RPE over Z2 minus MD1 over Z2 minus MD2 over Z2 minus MSD over Z2 dash minus ML over Z2 dash. The reason for Z2 dash is now the neutral axis has changed. So when the neutral axis has changed, you cannot call Z1 and Z2. It has to be a different Z value, right? Different Z, right? So this is the situation, right? And so you will get these 4 equations. These 4 equations. Right. So you get a big I composite value And so I have to make a small correction here. This Z1 dash and Z2 dash is I composite over this distance. And I composite divided by Y2 dash, I composite divided by Y1 dash. Right? Because now what is effective is the composite section. So Z1 dash will be I composite over Y1 dash, Z2 dash will be I composite over Y2 dash. And these distances are also different because now the neutral axis has changed. Neutral axis has changed. I value also has changed. I value is the I of composite. I of composite. But the locations are the pre-stress concrete beam, because we are designing the pre-stress. We are looking at the stressors in the pre-stress concrete beam. So because of that, although we are dealing with IC, still the distances will be to the top, bottom, and the top of the precast section. Precast section, right? So this is something you have to be very clear. So this IC, this is IC divided by Y2 dash, IC divided by Y1 dash, right? So those are the Z1 and Z2 dash lines. The reason is by adding concrete, we are going to make it a bigger section. It's a composite section. So when you are looking at the fibers, we have to look at the relevant fibers, the relevant fibers of the precast section, right? We are not extremely worried about the concrete we are going to place subsequently, because we can always adjust the strength of that particular concrete, right? So so these values will be Z1 dash will be I composite divided by Y1 dash. Z2 dash will be I composite divided by Y2 dash. And Y1 dash will be a smaller value, Y2 dash will be a bigger value than Y2. The reason is the distance to the centroid will now move away from the bottom fiber, right? So neutral axis will move away from the bottom fiber. The reason is we are going to get a thicker section now. Earlier, if the height is 700 millimeters, now the height is 850 millimeters. And we have more concrete as well. So we get a very strong, large section to carry the live loads and the superimposed dead load. So it's an advantageous situation because we are going to end up with very low stresses due to live. So that's the advantage of composite construction. So if you look at these four equations, these are the four equations that are applicable. Now you can see we can again draw a Magnus diagram. To draw the Magnus diagram, we have to convert it to the form that is PE over Z1 should be greater than minus P over A minus plus MD1 over Z1 plus FTT. So if you multiply it, because here you can see Z1 is a negative quantity, so the inequality will change. E should be less than minus Z1 over A plus MD plus FTT Z1 divided by P. So this is equation number 5. Equation number 6 is minus Z2 over A plus MD FCT plus FCT Z2 over P. Equation number 6. Next one is E should be greater than minus Z1 over A plus MD1 D1 plus MD2 plus MSD over Z1 dash. Here you get Z2, here you get Z2 plus ML over Z1 dash. So here you get Z1, here you get Z1 and plus, so here you have to say it is greater than, these are top fiber is going to fail in compression, so this should be less than F compression W. This should be greater than F tension at working conditions, right? So here you get plus F CW multiplied by the whole thing multiplied by Z1 over RP. So it's whole thing multiplied by Z1 over RP. So here you can write it again. It should be greater than minus Z1 over A plus MD1. So you can see here you get Z1, here you get Z1, MD1 plus MD2 plus MSD Z1 over Z1 dash plus M L Z1 over Z1 dash plus FCW times Z1, the whole thing divided by R. And the next equation will be, it should be less than, it should be, this is, it should be less than. And here also you get, it should be, just one moment. This is greater than, it should be less than, it should be less than, it should be greater than. It should be greater than, this is equation number 7. And the last equation will be, it should be less than minus Z2 over A minus Z2 over A plus, here you get MD1 plus MD2 plus M superimposed dead load Z2 over Z2 dash plus ML Z2 over Z2 dash plus FTW Z2 divided by R. Same equation. So only thing is now the equation is lengthy because we are having so many moments applied at different stages. So MD1 is applied at the transfer, MD2 is applied when we place the beam and pour concrete. Then superimposed dead load comes from the delay analysis, live load moment comes from the delay analysis. But for those, the Z values are different because now you have a bigger section resisting the moments. Plus whatever this FCW and FTW values. And you can see the difference between trans and working. Working gets RP, transfer gets. So we have 4 equations. 4 equation means we can draw a magnetic diagram, right? We can draw a magnetic diagram. So the same theory. So it's very easy because you can see even for a composite beam bridge, which looks complicated. The method is very simple. Method is the same as the earlier one. Minus Z1 over A minus Z2 over A. So equation number 5 says less than. So it goes this way. This goes this way. Equation number 5, 6. And you might get equation number 7 and 8 going like that. And you will get a feasible region. But before you mark the feasible region, we have to mark the maximum position where we can get the eccentricity, that is Emax. Emax. And that location is, if you look at the beam, look at the beam. If you look at the beam, the neutral axis will be here, and you can't place tendons beyond this point. So that is Emax. So this is Y2, this is Y1, and this is Emax. So we have to mark Emax also. The moment you do this, if you have selected the correct section, you will get a feasible region. You get a feasible region. Now what you do is, you select a point pretty close to this area. Why? Because this is the area that will give you the minimum pre-stress, and because it gives the minimum pre-stress, we can get an economical section. We can get an economical section. So that is the method. So basically, what you see is we are designing, we are using the same sign notation. Only difference between the simply supported case without concrete and the one with concrete is that when we use the one with concrete, we get composite action, and composite action will make the section more efficient because it's now bigger. Now it's bigger. It has a higher I value, and then because of that reason, the effect of live load stresses will be less. So we have an advantageous position because of the composite action. But we draw the manual diagram for our pre-stressed concrete beam, that is this beam. For this beam, we draw the manual diagram. And we have to find the pre-stress also for this beam, because all the other things are that come subsequently, which are not important for service conditions. Those are important only for the ultimate limit. So we can easily design a beam like this by drawing a manual diagram. And when you draw the manual diagram, we select the pre-stress as low as possible. And we come to this place because this is 1 OP and this is C. So 1 OP means where the more we go this way, we can get a lesser. So that's how you find the pre-stress force by using the manual diagram for the composite section. So designing a composite beam should not be considered as a difficult task. The only problem is it has long equations, much longer than the earlier case. The reason is we are adding so many loads at different levels. First we allow the dead load or the self-weight moment. Then we have to take account of the concrete, the weight of the concrete that we are pouring later. Then we allow the composite action to develop. Then we'll have a bigger I value and different Z values. And then the whole bridge or the whole slab will participate in resisting the superimposed dead loads, like the weight of the walkway, weight of the asphalt concrete, the handrails. Those are minute, but whatever it is, it will be the composite action. And then we get the very heavy live load, like a 120 ton or 180 ton truck proceed the bridge, and we get moments, but this has a very good torsional moment carrying capacity. So because of that reason, we get a huge load distribution. So basically, the structure cannot deform on its own, and so because of that reason, we are going to get a live load which is relatively low. Because the load is distributed everywhere and all the beams are now carrying the live load. So you get an efficient section, strong bridge, and above all, the most important thing is all these equations can be easily represented on a macro diagram. And that's a huge advantage, because the moment you draw the Magellan diagram, you can find the pre-stress. And if you have used loss ratio of about 30%, you can check the losses, but the chances are all those will be pretty okay. And if you are not very keen on optimizing to the limit, then if you assume 25% loss ratio and check the stresses, you will find it's all okay. Because if you get something like actual loss ratio as the 27%, and if you are going to allow this extra 3%, then you don't have to recalculate. You have assumed 30%, and actually is 27%. Let it be. You don't have to recalculate. So the other advantage is, for this type of sections, the guidelines have already been developed by various companies, so you can directly use the guideline. And if you know a little bit of drainage analysis, even a building engineer can easily become a bridge engineer. Because if then you will ask why the bridge engineering is so different. The difference is actually in that. It's in that. Now, what do you mean by attitude, right? So we have to understand, because there are specialized bridge engineers, and if you can so easily become a bridge engineer by understanding this type of thing, then why? So what is the difference between the building engineer and a bridge engineer? Building engineer generally knows about the loads. He has some idea, because he's working on a building, and he's working in the spans of 6 to 9 meter range. Bridge engineer, he has absolutely no idea about the loads. No idea. So he goes for huge loads like 120 tons to 180 ton loads. And he's dealing with 14 to 30 meters. Right? And then here in the building, analysis is fairly straightforward. Why? Because we know there's a grid of slabs, and now the loads are distributed. So we just do this and say the load of this area will come out to this beam. The load of this area will come out to that beam. Very easy. Bridge, we have to do a grillage. The loads can be placed, a truck can be like this, and then like this, because this can be the prime mover in a different angle, and the trailer in a different angle. So loads can be very complicated. So before the computers were available, actually this load transfer was a huge problem for bridge engineers to find the maximum bending moment. So actually speaking, there's no need to be so accurate finding the maximum bending moment, because we are designing for huge loads. But that's the way engineers have been trained. So there is well out of time. But today, if you look at Midas Civil or CSI Bridge, you can specify some loads and very easily get the answers. And sometimes, this can be even automated. Like, you can ask the program to find the maximum moment. So program will try all different types of positions and find the bending moment in the, which allow you to find MSD and MN. But in my case, I'm not very keen in finding, to be too accurate, knowing very well that, we already have various partial factors of safety. On what? Already assume huge loads. These are huge loads. Already we start with a huge load and then we apply factors of safety. So a minor inaccuracy in the bending moment is not going to cause any problem to the bridge. So the moment you get that attitude, you'll find that bridges also can be designed pretty easily, but you have to be very concerned about the foundation. Why? Because if something goes wrong, in a building we can always repair the building. At least we can say the loads are restricted or something, and we can even add the additional supports. But in the case of bridge, it is very different, because we are going to get the bridge placed either on piles or on a raft. So and also this may be subject to very heavy loads. So that also we have to appreciate, because we are talking about very massive loads, and also bridge is also heavy. Now in a building we might get 600 by 400 beam, but here we are talking about something, sometimes this can be 800 to 1000 millimeter deep. So we are talking about big loads and then big loads. So we have to be fairly concerned about the foundation conditions. And but whatever happens, again you have to look at some other advantage, because we are going to simply support the bridge. We know, the moment you simply support a bridge, what happens is the support, the variations that occur in the support has no effect on the bending moment that occurs in the bridge or the slabs. So when you look at that way, again you can see there are particular advantages. But in countries like England, when they constructed bridges like this, they found that during the winter they use de-icing salts, and salts come to these locations and create havoc on the in the piers. So what they thought was, okay, now this is not good, this is not good, we should make it continuous. So they thought, okay, let's make it continuous. So make it continuous. Make it continuous. So that for the live loads, continuous. Superimpose dead loads, continuous. All the other things, no composite action, simply support. So this actually, this particular arrangement improved the riding quality in a big way, because although we are using precast beams, the top slab is continuous, so you don't need any expansion or contraction joints. So they found that this actually works pretty well, because however, they found that as the spans increase, they run into problem, because now this is become too heavy to manage. So we are filling all this area with concrete. So the self weight is massive. Self weight of the structure, whole thing is massive. So when they found it, they actually moved to this solution. And this, by the time they moved to this solution, and later in the 80s or 90s, I think, they started looking at Y beams. Early 90s. So there's a gap, there's space, for any repair work, their space, inspection, their space can go up to 31 meters. This can go only up to 29 meters. So they call it M beam, and this because of this Y shape, they call it Y beam. And M beam, they are a problem. What is the problem? Now you don't have a torsional stiffness. You don't have a torsional stiffness. Earlier, huge torsional stiffness because we looked at a slab. But now we are not looking at a slab because the torsional stiffness, torsional shear flow in these members will occur within this space. So this lever arm is very small. It has no capacity. So then they said, let's analyze this as torsionless system. Let's analyze this as torsionless system, which means the torsional constant values are considered as very, very, very small in the grillage analysis. The torsional stiffness values are made extremely small in the grillage analysis. So what is the outcome? The lower level of load sharing, lower level of load sharing. That means each beam will have to carry a bigger load. Because when you have a heavy load on the beam, most of that heavy load has to be now carried by the beam. No lateral distribution, very little lateral distribution. But still they found, if you are going to use a slab of thickness more than 160 millimeters with double layers of reinforcement, then this is going to be a successful solution. So that's how the M-beam was developed. So now the time is 8:22. Can I ask whether you have any questions?
There's one
Any
question.
questions?
There's
Yeah,
one question.
there are a lot of things on the chat, but they are all. Sir, you told that ocean taking of pseudo deck is not necessary as they have. No, what I said was it's not critical. You can check it, but it's not going to be a major problem. But of course, when you have a skew bridge, it can become critical. But skew bridges, sometimes it can you can get some lifting and so on, and it's very true. It's a good question. And in right bridges, right bridge means the bridge is at 90 degrees to the abutment. The torsion is not a major problem. But whereas when you go for a skew bridge, that means the supports are not perpendicular to the direction of travel. They are at angle. Then of course that's a good question, good comment. And then there's another one. Mostly the other, kindly add your right. Okay. Right. So only one question, is that right?
Yes, sir. Yes, sir.
Right,
That
so
was the only question.
this slab bridges. So these days I like to adjust the slab, adjust the supports if at all possible, so that the skewness can be reduced. So basically, rather than having a huge bridge as one bridge, you can easily stagger the supports and have it as 2 or 3 parallel bridges. That way, you can minimize the effect of skew. But if you really want to go for a massive bridge, let's say 6-lane highway, where the supports are not perpendicular to the road. So supports are at an angle. So for example, we are talking about a road like this. River is like this. So these are skew bridge. Whereas these are right bridge. These are right bridge, these are skew bridge. So what I talked is something like this. These are right bridge. So you don't have a problem. Whereas here you can see there can be torsion. So in this kind of situation, I mean, if we are in the modern day, we have wide road, sometimes you can break the road into two, because in this way and this way. So when you have the skew, you can actually have the bridge apartments like this, and rather than having a narrow bridge, you will have a little wider bridge, longer bridge. So by doing various tricks like this, because when I say the support is like this, it doesn't mean that I'm going to construct anything, obstruct anything. What I'm going to do is I will put up something like this, 2 columns, and I will have something like that. So that way I can actually, avoid using a skew bridge. Or rather than using a skew bridge, I can easily have a bridge which is at right angles. So these are, I don't say that, you should not design skew bridges, but skew bridges, you have to be a little concerned, because they can be certain interaction in torsion, and it's better to provide a little higher amount of small diameter bars at closest space. So always, if you are not sure, the solution is small diameter bars, closest spacing. The reason is, the moment you put a lot of small diameter bars at closest spacing, automatically the concrete will find it pretty hard to crack, because concrete is supported by a reinforcement at closing. So that's the trick that we use. So it's a good question. Any other question like that? You can, I think unmute option is now available. You can ask directly. So, any other question?
It seems that's all, sir. Questions.
Yeah. So in that case, shall we wind up for today? And
Yes, sir.
next day, what we do is we'll discuss a little more about these bridges, how to provide the reinforcement and all that, and how we design the top slab. All those things we'll discuss a little bit, right?
Okay,
And
sir.
after that, so basically next day also, I think it might be okay if we spend little time looking at various aspects of this type of bridge. What do you think? Is it okay? Next week also we spend little more time, and
Yes.
then before we move to the next stage?
Yes, sir. That will be good.
Very good, right? So next week, I think we might be able to have a small demonstration on.
And sir, some participant is asking about the link slabs.
Link slab. What is that? Link slab? Link slab is you get two cantilevers, and that is supporting balance cantilever, and then you have a small slab in between. Is that right? Is that what do you mean by link slab?
I think so. Just the name is there in the chat box.
All right. So I think that comes only with this balance cantilever type situation. So basically, once we go beyond this composite, then the next stage will be to move to how to make the continuity. So next time we'll discuss the continuity aspect. How to make continuous bridges with composite construction, right? With precast beams. So beams are precast, bridge is continuous. And if you'll ask how about examples in Sri Lanka? Actually, we don't have many examples, because there are so many different ways of making the continuity. So in most of our bridges, we have actually used the easiest method. Even the very big bridges like Orugudavatta, we use that one, and then the late engineer Vijendra, who designed the bridges of A15 from Batticlaw to Trincomalee. There are about 5 bridges that Vijendra designed for access engineering. though he worked at Road Development Authority Design Office, but he did it at his private capacity, 5 bridges. Some of those are about 200 meters long with I-beams. And then we also had 2 bridges of 125 and Verugal bridge of something like 75 meters of length. So there are 5 bridges. He used the same method. So I can explain that particular technique. And also we also designed 2 more bridges on the A4 highway on the eastern coast. One is 125 meters long, the other one is 75 meters long. So I actually did the main calculation, and after that everything else was done by the engineer Vanikaratna, who is well known for tall building designs. So he did the bridge design as well. So basically we can discuss all those matters next time before we move to the next stage, that is the continuous construction. First, we'll look at how to make continuity with precast beams. How to have continuous bridges with precast beams. So that's going to be the title for next week.
Okay, sir.
Right? Okay.
And I would like to invite Engineer Shanika for the vote of thanks.
Good evening to you all. Hope you all had a wonderful session of 1.5 hours with lots of learnings. Today was the 8th session of the webinar series on structural design of highway bridges. On behalf of the organizing committee, I'd like to express our heartfelt gratitude to Professor Dishan Jayasinghe for his insightful and informative presentation.
Thank you.
Dear sir, it was really interesting, and I'm sure our participants gained a lot of valuable knowledge through your comprehensive explanations. We highly appreciate your efforts and time spent on enlightening us. Also, I'd like to mention that this webinar series had been a success owing to the valuable support of the CESC Chairman, Engineer Kamala Gunawardena, the IESL Secretariat, the Publicity Department, and the IT team. We'd like to thank them for their hard work in making this event a success. Also, we had around...
Yeah, go ahead, please.
Yeah, we had around 100 participants for today's session. So we really appreciate your participation and the insightful questions. So as Sir said, the next session will be on next Tuesday, that is the 2nd of May. So we hope to see you all there. Have a great week ahead. Thank you. Good night.
Yeah, thank you very much. And I will be sharing these handwritten notes with the committee. Okay.
Okay,
sir.
sir.
That
Okay, thank you very much.
Thank you, Shanika.
Okay,
Thank you, sir.
Thank you,
Shanika.
Thank you, bye.
Thank you, sir. Thank you.
Thank you.
Thank you very much.
Thank you.